Thanks. I thank very much Professor Lahar Sahil for kind invitation to talk in the frame of the International Congress on photocatalysis and for the environment. The general title of the Congress is related to the principles of green chemistry and sustainable chemistry. Professor Pietro Tundo is here in the auditorium. He is Venice University of Italy. He is pioneer in promoting green chemistry not only in Italy but all over the world. More specific, 3 years ago, created the MEGREC, the Mediterranean Network for Green Chemistry, in which 8 countries participate, from the south, Italy, Spain, Serbia, and Greece, and from North Africa, the Morocco, Algeria, Tunisia, and Egypt. It gives me much pleasure to be here with you in Constantine, the famous and magnificent city, which I visited yesterday, with a great history, and it seems that Constantine is a Greek name. As environmental chemist and analytical chemist, I have very interesting in chemical metrology, in science and environmental science, especially. This presentation is prepared with my PhD student, Theodoros Kouroumeliokis. Here you can see this nice picture. This, the National Kapodistra University of Athens, has a history of only 150 years, but this history is related to the history of the age of Plato and Socrates, and this is the 10 sciences which the Greek ancient people they named, and I can say some names of that. Philosophy, archaeology, history, mathematics, rhetoric and poetry, as well as legislation, medicine, theology, astronomy, and physics. Next slide refers to outline for my talk. After a small introduction, I will speak on measurement and quality, and then on chemical metrology, and more specific environmental sciences, and the instrumentation related to measurements in environment, and some words for perspectives to conclusion. The Philip Grossty, a businessman and writer, stated some years ago, quality begins with people, not with things. Before you are able to improve quality, you will have to change attitude of people to their job at each stage of business, of a business process. Leopoulos Dorogios, 6th century before Christ, stated in Greek language, metron ariston, and ariston is ine to metron. Metron means meter, is related to ariston, the velpiston, the optimum, not the maximum. And the velpiston, the optimum, is the meter. Albert Einstein later stated that if you cannot measure something, it does not exist. You can control, you can control what you can measure. Nowadays, there is a continuous progress in chemical metrology. We have to measure what is measurable to nowadays with certain reliability. And this is the new front of research, make measurable what cannot be measured today. This diagram shows the measurement which relate to the quality. If you have a problem, always we have problems in the environment, we need a solution. Analytical chemistry, environmental chemistry is a solution science, a science to give solution. In order to reach from problem to solution, you have to go some other steps. First steps, I don't have time to in details, is the design, the experimental procedure, which means that you have to define interferences, to select the methods, to establish validation, and so on. Then you have to conduct the experiment. This is very, very important. This is not important to produce numbers. It's important to calibrate instruments and equipment, to standardize the reagents, and gather the data. And after that, through chemometrics, we have to reduce or transform the data, to analyze statistics, to verify results, to interpret the results. So it's clear that if we have an analytical laboratory, if you are going to make analytical measurements, and then in this laboratory, you have to consider seriously all these factors: equipment and instrumentation, materials, different materials, chemicals. We have to choose the right methodology. We have to use chemometrics, and we have to have the right person. Chemometrics is very important nowadays. Years ago, the chemists consider only the materials, but nowadays we have to give much attention not to the raw data, but to the treated data through chemometrics. So it's obvious that the quality of measurement is related to analytical error of measurement. That is the sum, the test results minus the conditional true value is the error, and is the sum of random errors and systematic errors. If a measurement is repeated, each individual result will have its own association error. So, for this reason, we have to consider the measurement uncertainty and chemometrics. What is the meaning of uncertainty? It's a parameter associated with the result of measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. Chemometrics, like biometrics, is a new brand of chemistry, of practical chemistry, last 20 to 25 years, with interest in application of statistics, mathematics, and logistics in chemical data in order to design measurement process and experiments, acquiring the ultimate appropriate chemical information from the chemical data analysis. Why we need quality in the chemical measurements? Because we have to comply with legislative requirements and deliverables. And also we have in the open market high competition of quality aspects. The product has to have special quality, specific quality. The consequences of analytical errors we mentioned before is related to these three big fields: environmental sciences, environmental health, and industry and commerce. we have to see that in the meta studies, we are not doing only studies, but we have to monitor the different pollutants. Environmental health is a new branch of environmental chemistry which is related to health. It's not important nowadays to measure chemicals in different compartments of the environment. It's important to see what happens in the human body. We have to see the food toxicity, which food chains goes to the human body. Xenobiotics is a new field of study. We have to study xenobiotics to human body, which go through the water, food, air, and so on. Medical diagnosis is after xenobiotics to human body, and industry, of course, with a variety of products should be checked for their quality. Here it's clear now, the market, open market, we have consumer legislation and requirements and demands. Here we have the supplier, product services, the laboratories, and the laboratories should go through 3 different steps to accreditation. Now you can see a new term which is not often used in the literature, the laboratory science. It's the science which is applied to all kinds of laboratories. Laboratory here, different laboratories, chemical, biological, and so on. We have laboratories with suppliers, equipment, reagents, CRM. We have accreditation body, legislation. We have calibration laboratories and certification laboratories. In science, there is no democracy inside. It's obvious that the metrology is the science of measurements. Chemical metrology is the science of chemical measurements or chemical data. Metrology system covers all these facts, all these issues, the different organization, ISO and so on, units, characteristics, specification of analytical methodology, validation, which is quality assurance, and traceability. Traceability, here is the documents, basic documents and standardization organization, international, ISO, here is the website, the OECD, which developed the standard quality laboratory practice, the European Accreditation Guidelines, EA, the United States has the ASTM, and IFAC coordinates the international work of harmonization of different organizations. More information in Europe, you have the Eurochem, Cooperation of Analytical Chemistry in Europe, Eurolab for testing in laboratory, EA, Cooperation for Accreditation, Euromed, European Collaboration in Measurement Standards, IRM, Institute of Reference Materials Measurements. And internationally, we have CTAC, Cooperation on International Traceability in Analytical Chemistry. Now I'd like to point out some 10, 11 terms related to analytical methodology. Trueness. I cannot go all details, but I point out some of them. Trueness means closeness of agreement between the result of a measurement and the true value of measured value. True value can be defined by special laboratories, by accredited laboratories, and so on, with high quality instrumentation equipment. Precision is closeness to agreement between the results of a series or repetition. This is the standard deviation. Repeatability, reproducibility. Properness means capacity of the method to remain unaffected by minor changes of the procedure. Here you have specificity, it responds to a single chemical species, or an ion, sensitivity, linearity. Here there are two terms. Here, limit of detection, smallest quantity of a light that may be detected but not quantified, and the limit of determination, expression of smallest amount of light which may quantify, and traceability. Yesterday in the bottle water, I saw in the label the expression which say nitrate is 0. In analytical chemistry, in chemical metrology, there is no 0. There is only limit of detection or limit of determination. So there is no 0 in chemical metrology. There is a value lower than LOD, lower than LOD. Also, I like to inform the young, especially the young people, when we produce data, some people, if the measurement is lower than LOD, they don't report. That's wrong. Or they put 0. That's wrong. If you do some measurement, you have to report. But you have to put the right number. Because in statistics, we have to use these numbers in order to find the average and so on. So in this case, the rule is to put LOD divided by 2. By this way, we can use all the data. Traceability is a difficult term. It's a property of measurement result or the value of a standard to be linked to establish reference, general, national or international standards through an appropriate chain of comparison. Each heading and established as certain. So, if you are going to report in SI units, you have to go the through chains here, amount of content of X substance or solution, working standard, reference standard, and so we can report in SI units, not in our units. Quality assurance of chemical measurement. What is quality? Quality is characteristics of a product or service which confer the aptitude to satisfy the implicit or explicit needs. Quality assurance and quality control is related terms. This is for internal control of our laboratory. This can be done by external services. And in all cases, we have to have the right quality system, which have to go through quality assurance and quality control. See, if we have a quality system, it's not enough. We have to go to accreditation by external bodies. And this procedure goes through method validation, inter-laboratory comparisons, calibration of equipment, suitability of equipment, and competence of personnel. Personnel is very important. Now, two terms, accreditation and certification. Accreditation of a laboratory refers to competence to carry out specific tasks. Certification refers to assurance of conformity to specified requirements and tasks. In quality control systems, we have to go through method validation and method performance parameters, and we have to go through 3 steps within specification, with working correctly and adequately calibrated. Now, what is RM? Material of substance, one of more of whose property values are sufficiently homogeneous and well established to be used for the calibration apparatus, and the assessment of a measurement method or for assigning values to materials. And CRM means it's more specific term. It's reference material that's certified, accompanied by certificate. For this reason, we call it certified. One of more of course comparative values are certified by procedure, which establishes traceability to an accurate serialization of the unit in which the comparative values are expressed, and for which each certified value is accompanied by a certainty at a stated level of confidence. Now, here the use of certified material we can use for calculation of the method. Here it is the average value and the limits, and this is for the calibration curve, the calibration diagram. The OECD develops the so-called good laboratories practice years ago, and it's used in industry, it's used in commerce, in trademark. Good laboratory practice is a quality system concerned with the organizational process and the aspects. The parameters we used in the material science is physicochemical, pH and so on, major elements above 0.1% in the environment, like this, and trace elements in microgram, milligram, microgram, or even in traces. And these all elements should be determined in ultra traces level for some reasons. Here, words related to chemical species. I can use the term speciation, means chemical form of elements. Also, you can see here a new term. It's not, it's new one really. Metallomics. Metallomics is related to metals combined with proteomics. Proteomics, metabolomics, and metallomics. It's a new field. You have to consider all different oxidation states of the metallic compounds, protein compounds, metalloenzymes. This is metallomics, and it's a new field which is related to the studies in human body. We have also extracted all chemical forms, organic compounds, like dioxins, PCBs, pesticides, and so on. We have different types of methods. Calculable methods, this comes from calculation through measurement of weight or volume. Primary, this is very important, method with highest metrological quality, having few random errors and not systematic errors, and for which a complete estimate of the uncertainty may be obtained in terms of synthesis, gravimetry, and IDMS, isotope dilution MS, which is used in reference laboratories. Also, relative methods, comparative methods, I have to go better. Here is the selection criteria for the methods. Sampling is very important, the sampling. If you have a certain sample, it's okay. It's okay? Yes. And conservation of storage, and also we have the analytical methods, different aspects of analytical methods. Here is the end, all this I said in the previous slide. And now I'd like to present the Nobel Prizes for chemistry, for chemical instrumentation, to see how it's important. So in 1918, Richards awarded the Nobel Prize for accurate determination of atomic weight to to a large number of chemical species. 1923, Prickle for his invention of the method of microanalysis of organic substances, and Debye for diffraction X-rays and electron gases. Tiselius is known to us for his research on electrophoresis and absorption analysis, especially for his discoveries concerning the complete nature of serum proteins. And in 52, Martin and Sims for their invention of partition chromatography, 52. And chromatographic methods are very important in thermal analysis. Keirovsky for polographic methods of analysis, Libby for his method to use carbon-14 for the age determination of archaeology, geology, geophysics, and other substances of science. This technique is very important for the history of the civilization of the people. And Herbert for molecular spectroscopy in 1971. Klug for development of crystallography in electron microscopy, and for his structural elucidation of biologically important nuclei and protein complexes. In 1901, Ernst for high-resolution nuclear magnetic resonance spectroscopy. In 1955, Crutzen for atmospheric chemistry, the formation of the composition for ozone. Here is, this table shows the different and modern analytical techniques. It's showing liquid chromatography. Now, the last decade, we have to go from micro to nano analytical instrumentation. We have ultra fast and ultra high pressure in pharmaceutical analysis. Also, we have some achievements in mass spectroscopy and especially quantitative proteomics approaches. And here we have LCMS for metabolomics, metallomics, proteomics. Here is some known also spectrometric methods, which some of them are new one and used for characterization of different materials in the environment. So I can skip that because it's a conclusion of the previous slides. And now, here is the follow-up of the environment quality. In order to do that, in different reference sciences all over the world, we have to use validating methods. And all this can be done through international level works. So the perspective, the other side is research, fundamental research, training and exchange of new scientists and students through networks, center of competence. We have to educate the people in quality and metrology in order to be able to monitor samples in the environment. Here we have some references, books and journals. This is, I think, the first book written by John Kennan Taylor, in Quality Assurance of Chemical Measurement, which also translated into Greek language. This is a new book, very nice, Quality Assurance and Chemistry. We have a special journal, Quality Accreditation and Quality Assurance. Editor is DBM. And here, you can see here the conductor of the Philharmonic Orchestra. And you know, in musical harmony, we use meter. That means we use metron in musical instrumentation. use meter and metro in chemical instrumentation also. The scientists should be work together in order through chemical metrology to harmonize the environment with the nature. I start my talk with these slides and I will finish with that. Quality begins with people, not with things. Instruments laboratory. Before you are able to improve quality, you will have to change attitude of the people to their job in each stage of a business process. Thank you very much.
Thank you for this important presentation, and hope that the discussion will be more than fruitful. Est-ce qu'il y a des questions? Nous avons un peu de temps.